look up tonight, if you can. Find the moon, wherever it happens to be in its patient journey across your sky. That pale disk has been there your entire life, rising and setting with such regularity that you might be forgiven for thinking it ordinary. But the moon is not ordinary. The moon is, by any reasonable measure, impossible. Consider this. Every other rocky planet in our solar system either has no moons at all, like Mercury and Venus, or has moons so small they barely register, like the tiny captured asteroids circling Mars. And then there is Earth, a modest planet in the inner solar system, orbited by a companion so large it stretches the definition of what a moon should be. The moon is 1/4 the diameter of Earth. If Earth were the size of a basketball, the moon would be a tennis ball, and they would orbit around each other some 23 feet apart. No other planet has anything like this. Jupiter's largest moon, Ganymede, is enormous in absolute terms, but compared to Jupiter itself, it is just 6% of the planet's diameter. Our moon is 27%. The Earth and Moon are less a planet and its satellite, and more a double system. Two worlds bound together in a gravitational embrace that has lasted 4.5 billion years. And here is where it gets stranger. When scientists finally got their hands on lunar rock samples, they discovered that the moon is almost chemically identical to Earth's mantle. The ratios of oxygen isotopes, the fingerprints that distinguish one solar system body from another, are virtually the same. The moon is made of us, or we are made of it, or both are made of something that was once one thing. This is not what we would expect from a moon that wandered in from elsewhere, or one that formed alongside Earth from the same primordial cloud. This is what we would expect from violence, from cataclysm, from the kind of collision that rewrites the rules of planetary formation. The moon should not exist, and yet it does. Tonight, if the clouds permit, it will rise as it always has, indifferent to its own impossibility. This is the story of how it came to be, and what its presence means for the world we call home. To understand how we arrived at our current understanding of the moon's origin, we need to travel back through time, not to the formation of the moon itself, but to the human attempts to explain it. For centuries, the moon was simply there, a lamp in the night sky, a marker of months and tides, a companion so familiar that its strangeness went unquestioned. But as astronomy matured into a science, the question became unavoidable. Where did the moon come from? In 1878, a man named George Darwin proposed an answer. George was the son of Charles Darwin, the naturalist who had transformed biology with his theory of evolution. The younger Darwin turned his attention to the heavens, and what he saw troubled him. The moon was too large, too close, too perfectly matched to Earth's rotation to be coincidental. He reasoned backward from the physics he understood. If tidal forces were gradually slowing Earth's rotation and pushing the moon away, then long ago the Earth must have been spinning much faster, and the moon must have been much closer. Trace that process far enough into the past, and the two bodies would have been touching. Perhaps, Darwin suggested, they were once the same body. His hypothesis became known as the fission theory. Darwin imagined a young Earth spinning so rapidly that centrifugal forces overwhelmed gravity at the equator. A massive bulge formed, stretched, and eventually tore free, flinging itself into orbit to become the moon. The Pacific Ocean, that vast depression covering nearly a third of Earth's surface, was the scar left behind. It was an elegant idea, almost poetic. The moon as Earth's own child, born from the spinning body of its parent. The theory held sway for decades. In 1917, the British astronomer Harold Jeffreys became one of its most prominent defenders, working through the mathematics to show how such a separation might occur. But by 1930, Jeffreys himself had discovered what he believed to be a fatal flaw. The physics simply did not work. For Earth to spin fast enough to eject material, it would have needed a rotation period of about 2.5 hours. But the angular momentum of the current Earth-Moon system, even accounting for tidal evolution, was not nearly enough to support such a rapid spin. The numbers refused to cooperate. Darwin's beautiful idea began to crumble. Other theories rushed to fill the void. In the early 1950s, the American chemist Harold Urey championed a different explanation. Perhaps the moon had not come from Earth at all. Perhaps it had formed elsewhere in the solar system and wandered too close, becoming trapped in Earth's gravitational embrace. This capture theory had the virtue of explaining why the moon might be chemically different from Earth. A body formed in a different region of the solar nebula would carry different isotopic signatures, different elemental abundances. The moon would be a visitor, not a sibling. But the capture hypothesis had its own problems. For the moon to be captured, it would have had to approach Earth at just the right velocity and angle, losing enough energy to settle into a stable orbit without simply crashing into the planet or flying past it. The probability of such a perfect encounter seemed vanishingly small, and captured moons, like the small irregular satellites of Jupiter and Saturn, tend to have eccentric, tilted orbits. Our moon orbits in almost the same plane as Earth's equator, moving in a nearly circular path. It does not behave like something that was grabbed from passing traffic. A third theory proposed that the moon and Earth had simply formed together, condensing side by side from the same region of the solar nebula some 4.5 billion years ago. This co-accretion hypothesis was tidy and avoided the improbabilities of capture, but it struggled to explain why the moon has such a small iron core compared to Earth. If both bodies formed from the same material, they should have similar proportions of rock and metal. Earth's core is about half the planet's radius. The moon's core is less than a quarter of its radius, possibly much less. The moon is strangely light on iron, as if something had separated the heavy metals from the lighter rocks before it formed. By the 1960s, 3 theories competed for acceptance, and none of them fully worked. The fission model had the angular momentum problem. The capture model had the probability problem. The co-accretion model had the iron problem. Scientists were stuck. And then, in 1969, humanity did something unprecedented. We went to the moon and brought pieces of it back. The Apollo program was, among many other things, a scientific expedition. When Neil Armstrong and Buzz Aldrin descended to the Sea of Tranquility on July 20th, 1969, they carried with them the hopes of resolving a debate that had simmered for nearly a century. In a little over 2 hours on the surface, they collected 21.6 kilograms of rock and soil, the first samples ever returned from another world. These samples would not immediately solve the mystery of the moon's origin, but they would rule out most of what scientists thought they knew and point towards something far more dramatic. The rocks themselves were revelatory. Before Apollo, some scientists believed the moon had always been a cold, dead body, perhaps an undifferentiated chunk of primordial solar system material. The samples proved otherwise. The lunar highlands, those bright ancient regions visible to the naked eye, were composed of a rock called anorthosite, made almost entirely of a light-colored mineral called plagioclase feldspar. Anorthosites on Earth form in magma chambers where lighter minerals float to the top of molten rock to produce the vast quantities of anorthosite covering the moon's surface. The entire lunar exterior must have been molten at some point. The moon had once been covered by a global ocean of magma, hundreds of kilometers deep, churning and cooling over tens of millions of years. This was a clue, an enormous clue. For the moon to have been entirely molten at its birth, something must have supplied tremendous energy. A body forming gradually from cold dust and pebbles would not get hot enough. But a body born from a cataclysmic impact, assembled rapidly from debris heated to thousands of degrees, would be molten from the start. The Apollo samples also confirmed something troubling. The moon's oxygen isotope ratios were virtually identical to Earth's. In our solar system, different bodies carry different isotopic fingerprints, signatures of where and how they formed. Meteorites from Mars have distinct oxygen isotopes. So do asteroids from different regions of the belt. But the Moon and Earth share the same fingerprint, as if they were made from the same batch of material. This was precisely what neither the capture theory nor the co-accretion theory predicted. A captured moon should be isotopically foreign. A co-accreted moon should be isotopically similar, but also compositionally similar, with a large iron core. The moon had Earth's isotopes, but not Earth's iron. The data pointed towards something that had not yet been seriously proposed. In 1974, while the scientific community was still digesting the Apollo results, two planetary scientists named William Hartmann and Donald Davis made a suggestion that must have seemed almost reckless. What if the moon formed from a collision? Not a grazing blow that spun material off Earth's surface, as Darwin had imagined, but a genuine impact between Earth and another planetary body, a world large enough to fundamentally reshape both. Hartmann and Davis were aware that the early solar system was a violent place. Planet formation is not a gentle process. In the final stages, large bodies called planetesimals and protoplanets swept through the inner solar system, colliding, merging, and sometimes destroying each other. The terrestrial planets we see today are survivors of this cosmic demolition derby. What if one of those collisions had been particularly consequential? They proposed that a Mars-sized object had struck the young Earth at an oblique angle, ejecting a spray of debris into orbit. That debris, composed largely of mantle material from both Earth and the impactor, would have coalesced into the moon. The impactor's iron core, being denser, would have sunk into Earth rather than being ejected, explaining why the moon is so iron-poor. The energy of the impact would have melted everything, explaining the magma ocean. And because so much of the moon came from Earth's outer layers, the isotopic similarity would be natural. The idea gained traction slowly. In 1975, Alistair Cameron and William Ward developed more detailed models of how such an impact might work. By the time of a landmark conference in Kona, Hawaii, in October 1984, the giant impact hypothesis had become the leading explanation for the moon's origin. Scientists who arrived at that conference, holding to fission, capture, or co-accretion, left as converts to catastrophism. The moon was not spun off, captured, or grown alongside Earth. The moon was born from the destruction of two worlds. The impactor eventually received a name. Scientists call it Theia, after the Greek Titan who was the mother of Selene, goddess of the moon. The naming is fitting. In the mythology, Selene's mother was a goddess of sight and light, one of the original Titans who preceded the Olympian gods. In the science, Theia was a protoplanet that preceded Earth as we know it, a world that died so that our world and its companion could be born. What do we know about Theia? Less than we would like. By definition, Theia no longer exists as a separate body. It was destroyed in the collision, its material absorbed into Earth or ejected to form the moon. But we can infer its properties from the physics of the impact and the composition of its offspring. Theia was probably about the size of Mars, roughly half Earth's diameter and perhaps 1/10 its mass. It may have formed in roughly the same region of the solar system as Earth, sharing a similar composition, which would explain why Earth and Moon have such similar isotopes. Some models suggest Theia occupied one of Earth's Lagrange points, the gravitationally stable positions in Earth's orbit around the Sun, before gravitational perturbations from Jupiter or Venus dislodged it and sent it on a collision course. Other models suggest Theia formed farther out in the solar system and migrated inward. We may never know for certain. What we can model is the collision itself, and the models have grown increasingly sophisticated over the past 4 decades. The current best estimates place the impact at around 4.5 billion years ago, probably between 50 and 100 million years after the solar system began to form. Earth was still young, still growing, still being bombarded by smaller bodies. It may not yet have fully differentiated into the layered structure we know today. When Theia arrived, it did not arrive gently. The collision was not head-on. A direct impact would have been even more catastrophic, potentially destroying both bodies entirely and scattering their remains into a debris ring that might never have coalesced into anything recognizable. Instead, Theia struck at an angle, a glancing blow that tore into Earth's outer layers while allowing the cores of both bodies to eventually merge. The energy released was staggering. Temperatures at the impact site reached tens of thousands of degrees. Rock vaporized instantly. Both Earth and Theia were partially or wholly melted. The violence of that moment is almost impossible to comprehend from the comfort of a world that seems so solid, so permanent. In the immediate aftermath, what remained of Earth was surrounded by a cloud of debris, a disk of molten and vaporized rock orbiting the wounded planet. Over time, perhaps within a few hundred years, this debris began to cool and coalesce. Droplets of liquid rock collided and stuck together. Larger clumps grew by sweeping up smaller ones. Eventually, a single body dominated the disk, a molten sphere that would cool over millions of years to become the moon we know. This is the canonical model, the version of events that held from the mid-1980s until the early 2010s. But science does not rest, and the giant impact hypothesis has continued to evolve. In 2012, researchers Mattia Chuk and Sarah Stewart proposed a dramatic revision. What if the collision was even more energetic than previously thought? What if Earth was spinning much faster before the impact, completing a rotation in just 2 or 3 hours? In that scenario, a collision could inject far more material into orbit, potentially explaining why the Moon is so large and so similar to Earth. And then, in 2017, Stewart and her graduate student, Simon Locke, proposed something even stranger. What if the aftermath of the collision was not a planet surrounded by a debris disk, but something else entirely? What if the impact was so energetic that it created a new kind of object, one that had never been described before? They called it a synestia, from the Greek prefix meaning together, and the goddess Hestia, who presided over the hearth and home. A synestia is a structure that forms when a collision imparts so much energy and angular momentum that the resulting body cannot maintain a coherent shape. Instead of a planet with a disk, you get something like a spinning donut of vaporized rock, thousands of times wider than Earth is today, with no clear boundary between the planet and the disk. In a synestia, the Moon would not form from a disk orbiting outside Earth. The Moon would form inside the synestia itself, condensing from the vapor of the shared structure, inheriting its composition directly from the material that would eventually become Earth. If you find this difficult to visualize, you are in good company. A synestia has never been observed. It is a theoretical object predicted by physics, but existing only in computer simulations and the imaginations of planetary scientists. But the synestia model elegantly explains one of the most stubborn puzzles of lunar formation: why the Moon and Earth are so isotopically similar. In the canonical impact model, most of the Moon comes from Theia, not Earth. So we would expect the Moon to carry Theia's isotopic signature. But if both Earth and Moon condensed from the same synestia, from the same cloud of vaporized rock, they would naturally share the same fingerprint. The debate is not settled. Different research groups favor different variations of the giant impact hypothesis, and new data continues to refine the models. But the broad outline remains. The Moon was born from catastrophe, from a collision that nearly destroyed the world we now call home. Let us return to what we actually know, to the evidence that scientists have held in their hands and measured with their instruments. The Apollo program did not just return samples from one location. Over 6 successful landing missions, astronauts explored different regions of the Moon, from the ancient highlands to the younger volcanic plains called Maria. In total, they brought back 382 kilograms of lunar material, about the weight of a grand piano. Those samples have been studied continuously for more than 50 years, and they continue to yield new discoveries. One of the most important findings was the evidence for the lunar magma ocean. When scientists examined the highland rocks, they found that they were incredibly old, dating to 4.3 to 4.5 billion years ago, and composed almost entirely of plagioclase feldspar. On Earth, pure anorthosite is rare, found only in ancient mountain ranges, where it formed at the base of magma chambers and was later uplifted by tectonic forces. On the Moon, anorthosite covers the entire ancient surface. The only way to produce such quantities is to have an ocean of magma, hundreds of kilometers deep, in which lighter minerals floated to the top, while denser minerals sank to the bottom. The magma ocean model first proposed in 1970, just months after Apollo 11 returned, remains the foundation of our understanding of early lunar evolution. As the magma ocean cooled over millions of years, it crystallized in layers. Denser minerals like olivine and pyroxene sank to form the lunar mantle. Lighter plagioclase floated upward to form the bright ancient crust we see today. Between the crust and mantle, a layer of residual liquid became enriched in elements that do not fit easily into common minerals, elements like potassium, rare earth elements, and phosphorus. This material, given the acronym CREEP, has been found in samples from several Apollo missions and serves as a tracer of the Moon's early magmatic history. One particular sample has achieved a kind of fame among lunar scientists. During the Apollo 15 mission in 1971, astronauts David Scott and James Irwin discovered a small white rock sitting on a grey pedestal of soil, as if nature had placed it on display. This rock, later designated Sample 15415, became known as the Genesis Rock because it was thought to be a piece of the Moon's original crust, formed in the magma ocean and preserved for 4 billion years. The Genesis Rock is an anorthosite, almost pure plagioclase, and its crystallization age of about 4.1 billion years makes it one of the oldest intact rocks ever returned from another world. But the Apollo samples also created problems for the giant impact hypothesis. If Theia was a separate body that formed in a different part of the solar system, it should have carried a different isotopic signature. The oxygen isotope ratios, in particular, should have been distinct. When researchers analyzed the lunar samples with increasing precision, they found that the Moon and Earth were essentially identical in their oxygen isotopes, identical to a degree that seemed to require either extraordinary coincidence or a fundamental revision of the impact model. This became known as the isotopic crisis, and it drove much of the theoretical work on high-energy impacts and synestias that followed. More recently, studies published in 2016 using advanced laser fluorination techniques confirmed the isotopic similarity and extended it to other elements like titanium and tungsten. Some small differences have been found, suggesting that Theia did contribute material with a slightly different signature, but the overall picture remains one of remarkable similarity. The Moon is made from Earth, or from something that was once part of Earth, or from a mixture so thoroughly blended that the distinction has been erased. If you have followed this story so far, you might be wondering what happened to Theia. The impactor was destroyed in the collision, yes, but matter is never truly destroyed. The atoms that made up Theia are still here, somewhere. Some of them became part of the Moon, some of them became part of Earth. But where exactly did they go? For decades, scientists assumed that the mixing was complete, that Theia's material had been so thoroughly blended into Earth's interior that no distinct remnants could survive. The mantle convects slowly over billions of years, stirring itself like honey in a pot heated from below. Any chunks of foreign material should have been stretched, folded, and homogenized beyond recognition. And yet, deep inside Earth, there are structures that refuse to fit this picture. In the 1980s, seismologists made a peculiar discovery. When earthquake waves travel through the Earth, they move at different speeds depending on the density and composition of the material they pass through. By analyzing the arrival times of seismic waves at stations around the world, scientists can construct a kind of ultrasound image of Earth's interior. What they found was unexpected. Deep in the mantle, near the boundary with the outer core, roughly 1,800 miles below the surface, there are two enormous structures where seismic waves slow down. One lies beneath Africa, the other lies beneath the Pacific Ocean. These structures are called large low-velocity provinces, or LLVPs. They are continent-sized, each roughly twice the volume of the Moon, and they appear to be denser and chemically different from the surrounding mantle. For decades, their origin was a mystery. Some scientists suggested they were piles of oceanic crust that had subducted into the mantle over billions of years and accumulated at the bottom. Others proposed they were primordial features, remnants of the earliest differentiation of Earth's interior. No one could say for certain. In 2019, a young geophysicist named Chen Yuan was attending a graduate seminar at Arizona State University. The seminar covered the giant impact hypothesis, and the professor mentioned, almost in passing, that no trace of Theia had ever been found. Yuan had studied Earth's interior. He knew about the LLVPs, and in that moment, he had what he later described as a eureka moment. What if the blobs were Theia? Yuan spent years developing this idea, collaborating with colleagues across multiple institutions and disciplines. In November 2023, his team published a paper in the journal Nature, presenting their findings. Using high-resolution simulations of the giant impact, they showed that the collision may not have completely melted Earth's lower mantle. If the impact energy was distributed in a particular way, with most of the heating concentrated in the upper mantle, the lower mantle could have remained mostly solid. In that case, dense, iron-rich material from Theia's mantle would have sunk through the partially molten Earth and accumulated at the base of the mantle, like sediment settling at the bottom of a pond. The simulations matched the properties of the LLVPs remarkably well. The blobs have the right density, the right distribution, and they have apparently remained stable for 4.5 billion years, too dense to be stirred away by mantle convection. If this hypothesis is correct, then Theia did not disappear. Theia is still here, buried beneath our feet, a continent-sized corpse resting near Earth's heart. The implications are profound. The Moon and the LLVPs would share a common origin, both born from the same catastrophic event, one thrown into the sky and one driven into the depths. The collision that created our companion also reshaped our planet's interior in ways that may still influence Earth's geology today. Some researchers have speculated that the LLVPs might affect the pattern of mantle convection, influencing where volcanoes form and how continents drift. The ancient impact might still be shaping the world we live on. George Darwin, who imagined the Moon torn from Earth's belly, was wrong about the mechanism, but right about the connection. The Pacific Ocean does not mark the scar of the Moon's departure, but one of the great blobs, the one beneath the Pacific, may mark where Theia's remains came to rest. Darwin's intuition, born in the gaslit studies of Victorian England, pointed toward a truth he could not have known. We have spoken about the Moon's violent birth. Now let us consider what the Moon has given us in return. Because the Moon is not merely a companion in the sky, a source of light for poets and lovers. The moon is a guardian, a stabilizer, a silent partner in the project of making Earth habitable. Consider Earth's axial tilt. Our planet does not spin upright. Its axis is tilted about 23.5 degrees relative to its orbit around the Sun. This tilt is why we have seasons. When the northern hemisphere is tilted toward the Sun, it experiences summer. 6 months later, when it is tilted away, it experiences winter. The seasons drive weather patterns, growing cycles, and the annual migrations of countless species. Life on Earth has evolved around this rhythm. But axial tilt is not fixed. Planets wobble. The gravitational tugs of the Sun, Jupiter, and other bodies can cause a planet's axis to wander over time, shifting by degrees over thousands or millions of years. Mars, which has no large moon, experiences chaotic variations in its axial tilt, swinging from nearly 0 degrees to more than 60 degrees over geological time. When Mars tilts steeply, its poles receive intense sunlight, sublimating ice and potentially triggering dramatic climate shifts. When it tilts slightly, the equator bakes while the poles freeze. Mars is a world of climatic chaos, and its lack of a stabilizing moon is part of the reason. Earth's moon prevents this. The moon's gravitational influence acts as a kind of anchor, damping the wobbles that would otherwise accumulate. Over millions of years, Earth's axial tilt varies by only a degree or two, not the tens of degrees that Mars experiences. Our seasons remain relatively stable. Our climate zones remain relatively consistent. Life has had a predictable environment in which to evolve, and the moon deserves much of the credit. The moon also drives the tides. This seems obvious, but the implications are deeper than you might expect. Twice a day, the oceans rise and fall, pulled by the moon's gravity into bulges on the near and far sides of Earth. These tides are not merely a curiosity for beachgoers. They create the intertidal zones, those rich ecosystems where land meets sea, where life faces the daily challenge of submersion and exposure. Many scientists believe that tidal pools and coastal margins were crucibles of early evolution, places where the first complex life adapted to changing conditions. The tides may have helped drive the emergence of life on land. The sun also contributes to the tides, but its effect is less than half as strong as the moon's. The moon is much smaller than the sun, of course, but it is also much closer. And for tidal forces, proximity matters more than mass. Without the moon, Earth's tides would be driven solely by the sun, and they would be gentler, less dynamic, less capable of stirring the coastal waters and oxygenating the shallows. The intertidal zone would be narrower, the mixing less vigorous, the evolutionary pressures different. There is something else the moon has done for us, something that stretches across billions of years. The moon has slowed Earth's rotation. In the distant past, shortly after the moon formed, Earth was spinning much faster than it does today. A day may have lasted only 6 hours. The moon's gravitational pull on Earth's tidal bulges creates friction, and that friction acts as a brake, gradually slowing our planet's spin. Over 4.5 billion years, our days have lengthened from 6 hours to 24. The process continues today, adding about 1.4 milliseconds to the length of a day every century. It is imperceptible on human timescales, but over geological time, it has transformed our world. Longer days mean more stable temperatures. A planet spinning every 6 hours would have extreme temperature swings between day and night, with less time for the surface to warm and less time for it to cool. Life would have to cope with rapid, dramatic cycles. The moon's patient breaking has given us gentler days, more time for the sun to warm the land, more time for the heat to radiate away at night. We live on a slower, calmer world because the moon has been pulling on us ever so gently for longer than we can imagine. If you have ever looked up at the moon and felt a sense of connection, a sense that this distant body is somehow part of your world, you are right. The moon has shaped the earth in ways that make your existence possible. There is a device sitting on the lunar surface, placed there by astronauts more than 55 years ago, that is still working. It has no moving parts, no electronics, no power source. It is simply a panel of precisely angled mirrors, 100 corner cubes of fused silica, designed to reflect light back in exactly the direction it came from. This is the laser-ranging retroreflector, and it is the only experiment from the Apollo program that continues to return data today. The principle is simple. A telescope on Earth fires a laser pulse at the moon, aimed at one of the retroreflector arrays. The pulse travels across the void at the speed of light, bounces off the mirrors, and returns to Earth. By measuring the time elapsed between firing and detection, scientists can calculate the distance to the moon with extraordinary precision. When the experiment first succeeded on August 1st, 1969, the accuracy was about 7 meters. Today, with improved lasers and detectors, the accuracy is better than 1 millimeter. We know the distance to the moon more precisely than we know the distance between many cities on Earth. What has this precision revealed? Many things. The moon's orbit is not a perfect circle, but an ellipse, bringing it closer and farther from Earth as it travels. The moon wobbles slightly on its axis, a phenomenon called libration, which allows us to see slightly more than half of its surface over time. The moon has a small, partially fluid core, detected through subtle variations in its rotation. Einstein's theory of general relativity has been tested by lunar laser ranging, confirming that gravity behaves as predicted even across the gulf between worlds. But one finding stands out above the rest. The moon is moving away from Earth. Every year, the distance between us increases by 3.8 centimeters, roughly the rate at which your fingernails grow. This is not a measurement error or a statistical fluke. It has been confirmed by decades of observations, thousands of laser shots, millions of returned photons. The moon is leaving. This recession is not mysterious. It is a consequence of the same tidal forces that slow Earth's rotation. As the moon pulls on Earth's tidal bulges, Earth pulls back on the moon, transferring angular momentum from Earth's spin to the moon's orbit. The moon speeds up and moves outward. Earth slows down and the days grow longer. It is a trade, energy for distance, and it has been ongoing since the moon formed. In the deep past, the trade was faster. When the moon was younger and closer, the tidal forces were stronger and the recession rate was higher. Calculations suggest that shortly after the moon formed, it may have been only about 15,000 miles from Earth, compared to the 239,000 miles that separate us today. The moon in the Hadean sky would have appeared enormous, dozens of times larger than it appears now, dominating the heavens like nothing we can imagine. The tides it raised would have been catastrophic, washing hundreds of feet up the shores of whatever land masses existed, if any existed at all. Over billions of years, the moon has retreated and the tides have gentled, but the retreat continues. In the distant future, perhaps 50 million years from now, the moon will be far enough away that it will no longer be able to completely cover the sun during a solar eclipse. Total eclipses, those transcendent moments when the solar corona blazes around the black disk of the moon, will become impossible. Only annular eclipses will remain, rings of fire instead of crowns of light. We live in a special time, a brief window in Earth's history, when the moon happens to appear almost exactly the same size as the sun in our sky. This is coincidence. The moon is 400 times smaller than the sun, but also 400 times closer. The numbers happen to match for now. Eventually, billions of years from now, the moon will be so distant that the tidal interaction will weaken to near nothing. Earth's rotation will have slowed to match the moon's orbital period, and the two bodies will be locked in a synchronous dance, always showing the same faces to each other. But that is so far in the future that the sun will have begun to die before it happens. The moon will still be with us when our star begins to expand, when the inner solar system is consumed by fire. The partnership that began in violence will end in fire, unless some distant descendant of humanity finds a way to intervene. For now, the moon drifts away at the pace of growing fingernails, and the retroreflectors left by Apollo astronauts continue to measure its retreat, one laser pulse at a time. Let us pause here and consider what we have learned. The moon is not ordinary. It is a remnant of catastrophe, born from the collision of two worlds, carrying within it the blended material of Earth and a vanished protoplanet called Theia. Its presence has stabilized our climate, driven our tides, slowed our days, and created the conditions under which life could flourish. The same collision that created the moon may have left continent-sized remnants of Theia buried deep inside Earth, structures that geologists are only now beginning to understand. The moon is receding, slowly but measurably, and the precise measurements made possible by Apollo-era technology continue to refine our understanding of this gradual farewell. In the far future, the moon will be too distant to fully eclipse the sun. In the very far future, Earth and moon may lock into a synchronous embrace, forever showing each other the same faces. But for now, the moon rises and sets as it always has, indifferent to our theories, patient beyond our comprehension. There is something humbling about this story. The moon is so familiar, so constant, that we rarely stop to consider how strange it is. A world born from the destruction of another world, carrying within it the fingerprints of a planet that no longer exists. A companion that has shaped our world in ways we are only beginning to appreciate. A partner that is slowly leaving, so slowly that 100 human generations will pass before the change becomes noticeable. If you look up at the moon tonight, you are looking at evidence of a collision that nearly ended the Earth before it truly began. You are looking at a world that was once molten from pole to pole, covered by an ocean of magma that took millions of years to freeze. You are looking at a body that has been protecting us, stabilizing us, slowing us down for longer than there have been eyes to see it. And if you place your hand on the ground, you are, in a sense, touching Theia. The ancient impactor is still here, resting in the deep mantle, a ghost of a world that died so that we could live. The question that began this story was simple. Where did the moon come from? For most of human history, we had no answer beyond mythology and speculation. The moon was a goddess, a lantern, a wheel of cheese, a mirror reflecting Earthlight. It was not until the 19th century that scientists began to seriously investigate its origin, and not until the 20th century that we had the tools to test our theories. The Apollo missions transformed our understanding, and the giant impact hypothesis emerged as the leading explanation. But even now, more than 50 years after humans walked on the lunar surface, the details remain under investigation. The synestia model, the high-energy impact scenarios, the LLVP hypothesis, these are all active areas of research, subjects of ongoing debate and refinement. What we can say with confidence is this: the moon was not captured from elsewhere in the solar system. The moon did not form alongside Earth from the same cloud of dust and gas. The moon was not spun off from a rapidly rotating Earth. The moon was born from violence, from the collision of Earth and a Mars-sized body called Theia, approximately 4.5 billion years ago. The energy of that collision melted both bodies, ejected material into orbit, and created the moon we see today. The remnants of Theia may still exist, buried deep inside Earth, where they have rested for billions of years. The moon has been a partner in making Earth habitable. It has stabilized our axial tilt, driven our tides, slowed our rotation, and created conditions favorable for the evolution of complex life. Without the moon, Earth would be a different world, perhaps too chaotic for life as we know it to emerge. The collision that nearly destroyed our planet may have been the event that made it livable. And the moon is still with us, still influencing our world, still measurable by lasers bouncing off mirrors left by astronauts who are now old or gone. It drifts away slowly, 3.8 centimeters per year, and someday it will be too far to fully eclipse the sun. But that day is millions of years away. For now, the moon is ours, a companion born from fire and debris, a witness to the entire history of life on Earth, a reminder that we exist because of processes we can barely comprehend. Consider the sheer improbability of it all. For you to exist, listening to these words, a Mars-sized planet had to collide with the proto-Earth at just the right angle, with just the right velocity, at just the right time. The debris had to coalesce into a moon large enough to stabilize Earth's tilt, but small enough not to disrupt its orbit. The moon had to be close enough to drive tides, but far enough not to tear the planet apart. The isotopes had to blend in just the right proportions. The magma ocean had to freeze in just the right sequence. Billions of years of subtle gravitational interaction had to proceed in just the right way. Every one of these conditions was met, not because the universe cared about producing a planet with liquid water and breathable air and curious creatures who would one day walk on the moon and bring pieces of it home. The universe does not care. These things happened because physics allows them, and in a cosmos vast enough, what can happen eventually does. You are the result of a 4.5 billion year chain of events that began with the destruction of a world. So is everyone you have ever loved. So is every creature that has ever lived on this planet. The moon in your sky is a monument to that destruction, and also to the creation that followed. It asks nothing of you. It has no purpose beyond the physics that governs its motion. But if you look up tonight and feel a sense of wonder, a a sense of connection to something ancient and vast and improbable. That feeling is real. You are made of the same atoms that were forged in the collision, rearranged by billions of years of chemistry and biology into a form that can contemplate its own origins. That is not nothing. That is, in fact, everything. The magma ocean has long since frozen. The bombardment that cratered the lunar surface has mostly ceased. The moon turns its familiar face toward Earth, locked in tidal resonance, patient and unchanging on human timescales. The retroreflectors wait in the vacuum, ready to return whatever light we send them. The ancient anorthosites of the highlands glow pale under earthshine, rocks older than any on our planet, witnesses to an era when the solar system was young and violent. Beneath our feet, in the deep mantle, the remnants of Theia may still be settling, continent-sized fragments of a world that existed before Earth took its current form. The LLVPs have been there for 4.5 billion years. They will likely be there for billions more until the sun expands and the inner planets are consumed. They are the burial mounds of a protoplanet, memorial markers for a collision that no one witnessed. And above us, the moon continues its slow retreat, gaining 3.8 centimeters of distance every year, trading proximity for stability, exchanging closeness for time. The tides still rise and fall. Earth's rotation still slows. The relationship that began with violence continues with quiet, patient, cosmic grace. This is not a story with an ending, not really. The moon will be there tomorrow, and the night after, and the night after that. It was there before any human looked up and wondered. It will be there long after the last human eye has closed. What we have is not an ending but a snapshot, a moment in a partnership that spans billions of years, captured in the light of a single evening. We began with the question of how the moon came to be. The answer, as best we understand it, involves fire and collision, destruction and creation, violence on a scale that defies imagination, and patience on a scale that defies comprehension. A world called Theia struck the young Earth and ceased to exist as a separate body. From the debris, the moon condensed and cooled. From the impact, Earth inherited a stabilizing companion and, perhaps, continent-sized remnants buried in its depths. The collision that nearly ended our world's story before it began turned out to be the event that made the story possible. The moon that shouldn't exist does exist. It has been watching over us for 4.5 billion years, long before there were eyes to see it, long before there was anyone to call it a moon. It will continue watching long after we are gone, unless we find ways to persist that we cannot yet imagine. It is ancient beyond reckoning, born from catastrophe, indifferent to our theories and our wonder, and yet somehow ours. Tonight, if the sky is clear, it will be there. It will be there tomorrow night, and the night after. It has nowhere else to go, and neither do we. We are bound together, Earth and Moon, by gravity and history, and the remnants of a world that died so that we could live. There is nothing more you need to do tonight. The story has been told. The moon will keep its vigil whether you watch or not. Let your eyes grow heavy if they wish. Let your thoughts drift where they will. The cosmos will still be there in the morning, vast and patient, waiting for no one. The moon is rising somewhere. Perhaps it is rising where you are. Perhaps you can see it through a window, or imagine it beyond the clouds. It is enough. It has always been enough. Rest now. The moon will watch over you, as it always has, as it always will.